Lab 5, Finding mu-K, a science friction story by Robert L. Stewart. A toy car is pushed and released, coasting to a stop across a level tabletop. We say that friction stopped the car. Can we find the friction force using our Python code to determine the net force from motion data? Here is a vector model for kinetic friction. The surface contact force is shown and the force of gravity. The contact force is resolved into its normal component in the y direction and the friction component in the x direction. In the y direction, the net y force has a magnitude of 0. The normal force is equal and opposite to the weight force, which for this car is 2.45 newtons. In the x direction, only the force of friction acts, and it acts opposite to the direction of the velocity. So the net force is the friction force. We then take our x and y position from the observed motion of the car across the level tabletop and put it into our net force from motion data program, and we see that we do not get the expected net force pointing to the left as the object moves to the right. We get a changing net force in size and direction, and there is a perpendicular force component that is flip-flopping up or down. Why is this? Look at the y data. It fluctuates and is not 0 as we would expect for an object rolling across a level tabletop. So I modify the CSV file to make the y value 0, and I rerun the Python program. This time the net force is now along the x-axis as expected, but it is flip-flopping positive and negative. We have to look more carefully at our tracker data. I will look at the graph for the position time, and as you can see here, the motion looks fairly smooth, but there are slight variations, slight fluctuations as the object moves. This is the velocity, initial velocity, calculated by using x0 and x1 from the tracker data. Tracker can calculate Vx from position data just like we're doing in the program. And here you see a picture of that data right here. And the small variations here have grown to very large variations here. And I remember the caution from the lecture, Forces from Motion, that approximating derivatives only works when we minimize the uncertainties. And small differences yield big fluctuations. The data used in the examples in lecture was synthesized. What do I do with my data to see the friction force? How do I minimize the uncertainties in my data? Well, maybe I can use Tracker to solve this problem. Tracker can fit a curve to the data. Here you see a parabola fitted to the xt data for the motion of the car in the x direction. The value a here is half the acceleration value. Here you see a linear curve fit to the velocity showing the trend of the car slowing down. So this is the acceleration, and we get a value of minus 0.555 meters per second as the acceleration, which compares very favorably to the value that was obtained in the position time data. So I now, in my spreadsheet, create a column for smooth x position and smooth y position and import that as a CSV file into my net force from motion program, and I do indeed see a constant net force pointing to the left as the object moves to the right. And as you see, the force is constant. That force is the net force, the force of friction, 0.139 newtons, giving a coefficient of friction of 0.0567, which I can now place into a model using Newton's second law as shown here. Here is my initialization and my calculation loop showing the calculation of the forces. V hat is the direction of the unit vector for the velocity and used to calculate the friction. Here you see the run of the program. I replaced the familiar ball with a block to represent the car. Here's the friction, the normal force, and the weight force. Here's the final position. I've got all the positions and times in a CSV file, so I can compare the time and position of the observed data with the model data, and they match very well, except at the very end where there's about a 2.5% difference. I also ran my Python code with Newton's second law to plot an x velocity time graph, and I calculated the slope of that and compared that to the slope of the linear regression in the tracker model, and found that they are less than 2% apart. What does this mean? I used the fundamental principle of Newton's second law to not only see the friction, but to model the motion of the object under friction, and I can use the coefficient of friction, kinetic friction, determined in other physical systems, and I learned a lot about measurement uncertainty. Here, there are the experimental uncertainties, and this is the end of Lab 5, but not the fun. What about Lab 6 or continued adventures? Thank you.